Impulse. All right. Starting off with the definition. Impulse is a change in momentum. Okay, so we need to make sure we're clear on what momentum is. So, momentum. What is momentum? Can you just give me the formula?
Movement.
P equals mv.
P for momentum equals mv, mass times velocity. All right, when we defined momentum, it was inertia in motion. So an object in motion stays in motion at a constant velocity. That's its momentum. Well, now we're talking about changing that momentum. Now this change, when we're talking about impulse, we're talking about something that's almost instantaneous. We're talking about a very, very rapid change. Well, if we're talking about changing the momentum, we have to change either the mass or the velocity. If we're going to change one of those very, very quickly, are we changing the mass or are we changing the velocity? Okay, so momentum is mass times velocity, and impulse is an almost instantaneous change in the momentum. What's most likely changing is the velocity, because mass is not something that changes very quickly. Okay? So, when we're talking about that change, we're talking about a change in the velocity. So, if we're talking about a change in the momentum, we're talking about changing from one constant velocity to another constant velocity fairly quickly. Okay, so it's the speed up or it's a slow down. But for our class, we're going to simplify it, and we're going to just talk about it in a positive sense of the term. All right, the next paper, we're going to glue it in after we write it. So write on it first, then glue it in. Okay, now here's something really cool about impulse that we have not had before. We have two formulas that give you the same answer. It's really cool. So, we have uppercase J. All right, that I don't really care for the font, so if you want to make it look like an uppercase J, that is not joules. That is impulse. Because this is a formula symbol, not a symbol for units of measure. All right, in order to get the impulse, I need to take F, what's F stand for? Force. And multiply it by delta T, which is? Change in time. So what that means is we need to multiply the force that was applied and the amount of time, for the amount of time it was applied to figure out the impulse. All right, that's one formula. What are units of measure for time? Seconds. Units of measure for force?
Newtons.
Newtons. So my units of measure for impulse are newtons times seconds. All right, that's one formula. Here's the other formula.
Interruption.
Impulse is also mass times change in velocity. M for mass, delta V, change in velocity, and the J, impulse. All right, what are my units for velocity? Meters per second. What are my units for mass? Base units, kilograms. So impulse is also kilograms times meters per second. Does that look vaguely familiar?
Yes, it does.
What are those the units to measure for?
Speed.
Momentum. All right, which makes sense because impulse is a change in the momentum. Just like a change in the velocity is meters per second, just like velocity is meters per second. Change in momentum has the same units of measure as momentum, kilogram meters per second. Now, I'm going to show you guys what's called a proof. All right, you do not have to put this in your notes, but being pre-AP students that you are, this is something, there's not going to be space on this page, so if you want to write it down, you're going to have to write another page because we are going to use this whole thing front and back. No, not the oops page. We're going to be using the oops page. On your piece of paper. All right. Okay, so what this is saying that force multiplied by time is equal to impulse. Mass multiplied by change in velocity is equal to impulse. So force multiplied by time is equal to mass times the change in velocity, which Newton seconds therefore must be equal to kilogram meters per second. I'm going to prove to you that that is true. All right, so I'm proving to you that Newton seconds is equal to kilograms times meters per second. Does everyone understand what I'm trying to prove?
Yes.
Okay. So, all right, newtons. What are we measuring with newtons? Force. All right. What's the formula for force? Mass times acceleration. All right. What are my units for mass? Kilograms. What are my units for acceleration? Meters per second squared. And now I'm going to bring this seconds down here. So kilograms times meters per second squared times seconds. All right, is equal to kilograms times meters per second. Does everyone follow so far? Yes? Okay. Now, algebraically rearranging this. You see that seconds squared is in the denominator here, and everything else is multiplied? We can rewrite that. Kilograms times meters over seconds squared like this, times seconds. And now I can do that. Okay? Now, watch what I'm going to do next. Kilograms times meters per second, times meters times seconds, divided by, what's seconds squared mean? And we multiply what by what? Seconds multiplied by seconds, right? Now if I have s in the numerator and s in the denominator, they cancel each other out. So now we have kilograms times meters over seconds. And again, I can rearrange that as kilograms times meters per second, which is equal to kilograms times meters per second. Okay? Now, I am not going to ask you to do that proof anywhere. I just want you guys to see that. This is how physicists think. Mathematicians and physicists think this way. They go with the units of measure and they prove that they did their math right by doing this sort of a thing with their units of measure to make sure that they got the right thing. Okay? Like I said, this is how really mathematicians and your physicists, they excessively nerdy way of thinking. Okay? If you have great algebra skills, this is really obvious and easy for the rest of us. It's like, oh, great. Okay, moving on. So, you don't have to have that in your notes. You don't have to do that. Just so you are aware of it existing. All right. Just wanted to prove to you that this exists. All right, we're going to glue this in. I want you to glue it slightly to the left. Just a little bit of glue. All right. Slightly to the left because I want to write something to the right. Okay, so you know how we talked about velocity, positive, negative, impulse, positive, negative, conservation of momentum, blah, 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 conservation of momentum, blah, blah, blah. All of that. To keep this simple and to be able to teach this in 1 day rather than 2 days, we are going to keep our change in velocity positive. Final velocity minus initial velocity, absolute value. Okay? So if you're speeding up or whether you're slowing down, we're going to keep that change in velocity positive for our class. If you go on to take AP Physics, you'll do positive and negative there. Okay? All right. All right, the next piece of paper is this one. Again, we're going to write on it and then glue it in. This, hopefully, helps explain, clarifies this whole idea that these two formulas are the same thing, what that means in a real life scenario. Okay? So, here we go. Zoom in there a little bit. Okay, we have an example. A 25 kilogram shopping cart is moving with a constant velocity of 4 meters per second. A force of 10 newtons is applied for 5 seconds. The shopping cart now has a constant velocity of 6 meters per second. Okay, so the object before, our shopping cart. Before the force was applied, what was the mass of the shopping cart? 25 kg. What was the velocity before the force was applied? 4 meters per second. Okay, so what was the momentum before? Mass times, momentum is mass times velocity. What's 25 times 4? 100 kilogram meters per second. Okay, so this is the before. All right, force is applied. How much force was applied? How strong was that force? 10 newtons. How long did we apply that force? 5 seconds. So 5 seconds is the almost instantaneous. In some examples of impulse, that can get down to fractions of a second. Okay? But 10 newtons applied for 5 seconds. Now that we've applied that, while we applied that extra force, its velocity increased. So what's its velocity after that force was applied? 6 meters per second. What was the mass after the force was applied?
25.
Still 25. The mass was unaffected by that change. What's 25 times 6? Mass times velocity, get the momentum. 150 kilogram meters per second is the momentum after the force was applied. Okay? So, there we go. Information applied. Now, let's analyze this a little bit. There are 3 ways we can calculate the impulse. Remember, impulse is a change in momentum. Class, repeat after me. Impulse, is a change in momentum. Wonderful. Okay, so change in momentum, delta P. Delta P is final momentum minus initial momentum. So, what was our final momentum? 150. What was our initial momentum? 100. 150 minus 100 gives us 50 kilogram meters per second. All right, the formula from up here, all right, impulse is mass times change in velocity. Mass times change in velocity, which is the same thing as mass times the final velocity minus initial velocity. So here we go. What's the mass of the cart? 25. What's the final velocity? What? Final velocity? 6 meters per second. What is the initial velocity, class? 4 meters per second. All right. So we have order of operations. These are in parentheses. What's 6 minus 4? 2. What's 25 times 2? 50. Kilograms times meters per second, because we did mass times velocity. All right, the third way we can do it is force multiplied by change in time, this formula right here. Okay, so here we have, what force was applied to the cart? 10 newtons. All right. For how much time was that force applied? 5 seconds. What's 10 times 5? 50. Newtons times seconds. Now, do you guys see the pattern?
Yes, I do.
3 different ways to measure it. 50, 50, 50. So it doesn't matter how you measured it. You still get the same answer. So based upon the information provided in a problem determines which formula you're going to use. And really it usually comes down to these two formulas. So if you're going to use this formula or this formula based upon what information is provided in the problem to solve the problem. But check that out. I mean, I think that's really cool. Two completely different formulas. I mean, force and time are not mass and velocity. But yet, we can use them, those two formulas, and we get the exact same answer. So cool. Okay, maybe I'm a nerd, but I just think that's really cool. All right. So go ahead and glue that in. Don't need a lot of glue. A little, it'll stick forever. All right. Now, what makes this lesson pre-AP versus just regular physics students? No, we have more to learn. We need to expand upon this a little bit.
I hate these labels.
Okay? So, we are now going to go to the oops page. Okay, so we're talking about impulse. Now, impulse is a change in momentum. Yes, we all agree?
Yes, ma'am.
Now, we've talked about conservation of momentum in a system. But if you look at the conservation of momentum in a system, like two different cars crashing, that sort of thing, or take that and now just observe one car and its change in momentum, the impulse applied to that vehicle in the collision. So impulse and collisions are closely related. Okay, the momentum in the system is conserved, but the momentum of the individual objects in the system does change. All right, so collisions, conservation of momentum. So we talked about conservation of momentum, that's great, but I didn't show you this because first you had to understand impulse, blah, blah, blah. Here we go. So let's look at a typical inelastic collision. We did this one in the lab. All right, so we have two cars same mass coming at each other with the same velocity. We'll say 2 meters per second. All right, so give them the same mass of 5 kilograms, 2 meters per second. Those two cars head-on collision. So when we're in the lab, we have the two cars without any weights. They head-on collided in an inelastic collision. What happened?
They stop.
They stopped. This is my favorite collision. I think it's the coolest thing in the world. They're both moving, they hit, and they just stop. So cool. All right, so they collide 5 kilogram into 5 kilogram, and they just stop. All right? They are at rest. So, by the fact that they stopped, and you consider the fact that they were the same mass, same velocity, well, same speed, opposite directions. Remember, going to the left is a negative velocity. So, what is the net momentum of this system? 0. Okay? To me, this is just like, wow. Like, oh my gosh, that's so cool. So, take that scenario, and now we're going to do it in reverse. Which kind of sounds like weird, like, how do you reverse that? Let me show you. So, on our lab carts, You guys remember that cool little button, and if you hit it, the little thing pops out?
Yeah.
Everyone kind of plays like, ooh, this fun, right? That, the purpose of that was to do exactly this, reverse that experience. Probably not, but we have a different lab. Okay? So, explosion. All right, some sort of force exploding, and these two now separate. Okay? Masses stay intact, going opposite directions. This one has -2 meters per second. This one's going to have a +2 meters per second. All right? They're moving away from each other. So, my question is, what's the net momentum of that system?
10? No.
2.
Isn't it the same as the first one?
Exactly, because it's the reverse. So what's the net momentum?
0?
0.
What? Oh, because it's a negative and a negative.
A negative velocity and a positive velocity, so that's a -10, that's a +10. Add those together, what do you get?
0.
0. Okay? So it's the exact same scenario here where they're colliding and they stop, inelastic collision. Combined explosion separates them. Okay. So inside of a gun, if you could cross-section a gun, and you see the bullet sitting in the chamber. Okay? We talked about this once before, this example, when we were talking about Newton's third law of motion. Okay? So we're now pulling in Newton's third law of motion with impulse and conservation of momentum. Okay? So we have a bullet inside that chamber. Gunpowder is explosive. You ignite it and it goes boom. So we create an explosion. But that explosion is going to push in the two objects. Object 1 being the gun, object 2 being the bullet with the same force. That's why guns are heavy. Lots of mass, less acceleration. Bullets, not a lot of mass, lots of acceleration. Yes? So that explosion is going to happen in that tiny little space, causing those two objects to move opposite directions.
That's crazy.
Yes? So if your gun and your bullet have the same mass, they would move with the same velocity, which would be a bad thing for your hand.
It blows over, isn't
Oh, is that what it, like in the olden times, the gunpowder and then they go.
Yes, because the gunpowder before was not inside the bullet. It was gunpowder that was placed behind a ball of steel. Does that make sense? Okay.
That's crazy.
Which was a little bit easier to transport, because you could go back and recover the ball of steel if you needed to.
Oh, you said was right.
Yep. But they weren't very accurate. You shoot it and it goes approximately there. So. All right. So this is what we're talking about here. These kind of examples here. So a slightly larger example rather than a bullet, but still on that same sort of mentality, a cannonball. This is how cannonball work. They put a bunch of gunpowder here. And the little fuse here that they light, it lights the gunpowder that's sitting back here and causes the explosion. The cannon moves slightly back, but because the ball has a lot less mass, it shoots out. But the momentum of that system before the gunpowder goes off, the net momentum of the system, is 0. All right? Net momentum of the system after is still 0. That momentum is conserved, but we're dealing with an impulse. This is a very, very, very instantaneous change in velocity. Yes?
So the impulse is 0 all the way, or are you in the point?
No, the impulse of the individual objects, the impulse applied to
Oh.
this and the impulse applied to that are the same. They're just going opposite directions, same magnitude. So when we're talking about impulse, we're talking about a single object looking at just like the ball or looking at just the cannon, but the momentum of the net momentum of the system is conserved, is 0. Yes?
Yes.
All right. So that's the idea behind it. There is your formula chart. So let's take a look at this formula chart. Lots of formulas. Okay, let's look at that right there. Impulse is force multiplied by change in time. The two formulas below it, it's the same formula, just rearranged to solve for the force or to solve for the change in time. Okay? Next column, we have impulse is mass times change in velocity. And then below it, that formula rearranged. Yes? Now, what we were talking about earlier, force multiplied by change in time is equal to the mass multiplied by the change in velocity. That's setting those two formulas equal to each other because they both equal the momentum. And now you rearrange that formula to solve for each of those variables. The mass, the force, the change in velocity, or the change in time.
Can I use a triangle?
You don't need the triangle because I already did it for you. This is where you'd use the triangle. I've already done it for you. Okay? So this exact formula chart will be on your quiz.
When's the quiz?
Considering we've got testing tomorrow, quiz probably won't be till Thursday.
Oh, hell no.
Go and get that glued in,
No.
and that's your journal entry.